So good morning students. So the low power design in logic level, we are going to see how the signal gating technique is used to reduce the power. Signal gating. What is meant by signal gating? Signal gating refers to a class of general techniques to mask unwanted switching activities from propagating forward, causing unnecessary power dissipation. The probabilistic techniques are often used for switching activity analysis. The simplest method to implement signal gating is to put an AND OR gate at the signal path to stop the propagation of the signal when it needs to be masked. Another method is to use a latch or flip-flop to block the propagation of the signal. Sometimes a transmission gate or tri-state buffer can be used in place of a latch if charge leakage is not a concern. The various logic implementation of signal gating is shown below. So this is AND gate, tri-state buffer, latch, transmission gate. So these four act as a signal gating to reduce the power in logic circuits. The signals at the bottom of the circuits are control signal. So this one and this one are control signals used to suppress the source signal on the left from propagating to the gated signal on the right. So the signal propagating from left to right can be controlled by the enable signal, this one. Okay, so that is called signal gating. Logic encoding. What is meant by logic encoding? The logic designer of a digital circuit often has the freedom of choosing a different encoding scheme as long as the functional specification of the circuit is met. For example, an 8-bit counter can be implemented using the binary counting sequence or the gray code sequence. Different encoding implementation often lead to different power, area and delay trade-off. The encoding techniques require the knowledge of signal statistics in order to make design decisions. The next slide discusses some techniques for using different logic encoding to achieve low power consumption. Binary versus gray code counting. Consider a n-bit counters implemented with binary and gray code counting sequences. The counting sequences of the two counters shown below. This is binary code, this is gray code. The sequence is given 0 to 7. This is also 0 to 7. Okay. Number of toggles. Toggles means the 3 bits. So here 3 bits. Okay, here only one bit has to change. Here no bits. Here one bit, that is 0, only the 0 to 1. Here 3 bits. Here 1 bit. Here 2. Here 1. If you take the gray code, only there will be one bit change. From this to this, one bit change. From this to this, one bit change. From this to this, one bit. So the previous state and the present state, there is equally only one change. Okay, but it's not like that. You take from 111 to here. So all the 3 bits must change. Compared to this and this 1 bit, this and this 2 bit, this and this 1 bit, this and this 3 bit, this and this 1 bit, this and this 2 bit, this and this 1 bit. Okay, this is called the number of toggles. But if you take the gray code, only 1 bit change if the sequence changes from 0 to 1, 1 to 3, 3 to 2, 2 to 6, 6 to 7, 7 to 5, 7, 5 to 4. Okay, so this is binary coding way to design the counter, 3-bit counter. This is a gray code technique the counter is designed. So the power can be minimized by the using the design of gray code counting. So binary versus gray code counting. Toggle activities of binary versus gray code counter. Number of bits, number of toggles for binary 2 into 2 power n minus 1, for gray only 2 power n. So Bn divided by Gn, you look at it, okay, the ratio, okay, when n is large, the binary counter has twice as many transitions as the gray counter. Since the power dissipation is related to toggle activities, a gray counter is generally more power efficient than a binary counter. The next concept is bus invert encoding. So what is meant by bus invert encoding? Bus invert encoding is a low power encoding technique that is suitable for a set of parallel synchronous signals. Example of shift buses. The architecture of bus invert encoding is illustrated below. You have a register, okay, invert pass the source data directly, this is exclusive, or invert pass one output is, this is polarity decision logic. This output is goes to the exclusive, okay, it has a bus register, polarity signal, that signal goes to input of this invert bus, this is data bus, okay, that you have a feedback, we will get whatever the data, we will get it at the received data. At each clock cycle, the data sender examines the current and next values of the bus and decides whether sending the true or the complement signal leads to fewer droppings. Since the data signals on the bus may be complemented, an additional polarity signals is sent to the bus receiver to decode the bus data properly. The assertion of the polarity signal tells the receiver to invert the received bus signal. So you take a number of bits, 2, 4 like that, regular bus, 1, 2, 4, 8, invert bus, okay, this is expectation of Q, okay, this is power Q, invert divided by regular ones, you look at it. So the efficiency of bus invert coding under uniform random signal can be estimated.